All right. Good evening, everyone. My name is Sarah Cocaro. I'm the Assistant Director of Environmental Affairs for the town of Greenwich. And on behalf of myself and my colleague, Myra Klockenbrink, Chair of the Land and Water Sector of the Greenwich Sustainability Committee and co-chair of the Greenwich Pollinator Pathway, we welcome you to our webinar tonight, Student Voices on Sustainability, Greenwich winners of the 2023 Connecticut Science and Engineering Fair. We extend a warm welcome to each of our student panelists for generously donating their time, and we thank our community partners for their promotional support. A special thanks to Dulcie Stanton from the Cos Cob Library, who is navigating the tech behind the scenes tonight. A few housekeeping items. The program will be about 90 minutes with roughly 25 minutes at the end for questions. Please put your questions in the Q&A located at the bottom of the screen. You can also use the chat function if you'd like to talk to us. This webinar is being recorded and it will be posted on the Cos Cob Library website. If you are a Greenwich resident interested in learning about the many sustainability initiatives happening here in town, please check out the Greenwich Sustainability Committee town website page or the Facebook group. We will also drop a link into the chat to access the newsletter. But I can't speak highly enough about it. Please subscribe, share it, check it out, share with your friends and family. It's a great compilation of everything sustainability going on in and around Greenwich. It's really well done. Tonight, we're convening Greenwich Middle and High School student winners of the 2023 Connecticut Science and Engineering Fair. The Connecticut Science and Engineering Fair brings together students, teachers, faculty, parents, engineers, and scientists in the hopes to interest young people in careers in science and engineering through recognition of their science achievements. Greenwich had 18 winners, highlighting the breadth of interest in areas and an amazing achievement. Congratulations to each and every student on your hard work and accomplishments. We are so honored to have you all here tonight. So sit back, settle in, and enjoy the discussion.
Thank you, Sarah. Our first speaker tonight is Caitlin Tice. She is a sophomore at Greenwich High School, and she won first place in applied technology and an invitation to this year's National Genius Competition for her presentation tonight. Caitlin, please begin.
Hello, my name is Caitlin Tice, and I'm excited to share my project with you. My project was the synthesis and investigation of metal organic frameworks for the purpose of atmospheric water harvesting. Currently, there are over 2 billion people who lack access to clean water, and there is just obviously a great need to develop like a novel approach to solving this crisis. One promising solution is to pull water from the air using metal organic frameworks, also known as MOFs. These materials are relatively new, and their study has many highly promising applications as they are very porous materials with chemical and structural properties that enable them to soak up molecules such as water onto their surface, which later can be released. The goals of this project were to 1, synthesize MOFs, 2, analyze their water harvesting capabilities under different conditions, 3, project the total amount of water that could be harvested, with 4, a simple and low-cost working model of a water harvesting system. The MOF synthesized for this project was modeled after MOF 303, which was created by Omar Yagi. Several modifications and alterations to the process were made given the limitations of a school lab setting. First, 3,5-pyrazole dicarboxylic acid monohydrate was mixed with lithium hydroxide and aluminum chloride, and the resulting precipitate was heated. The material was analyzed and tracked throughout the synthesis process using electron microscopes and spectrometers such as FTIR, EDS, and SEM. So figures 1 to 3 show the MOF before it was washed with water. As you can see, there is a strong presence of residual salts, but a unique structure has started to form. The MOF was then washed with water to eliminate these residual presences. So figures 4 to 6 show the moth before it was washed with methanol in a sock slip apparatus. The finished moth formed water-absorbent ionic crystallite structures constructive of organic linkers such as carbon, nitrogen, and oxygen, and aluminum ions. After examining the moth under an electron microscope, it's shown to have a vast surface area, which differs from moth 303's spherical clump-like shape, and therefore which has a smaller surface area. To test the water absorption capabilities of the newly synthesized moth, a novel methodology was used. A glove box was set up containing a relative humidity indicator, a scale, and the metal organic framework. I then exposed the moth to different humidities ranging from 30%, a more arid environment, to 88%, a more tropical one, and measured the of water absorbed at each condition over 18-minute intervals, which was found to be the most efficient time. The moth was capable of quickly absorbing water in a logistic growth-like function, which was dependent on relative humidity levels. The graphs also highlight the rapid absorption kinetics of the material. On the molecular level, figure 17 compares the dried moth, the black line, to a wet one, the red line. The dip in the spectrum indicates that there is a much stronger presence now of H2O within the compound. Next, I tested whether the moth could maintain stability over numerous absorption and desorption cycles, which would be necessary in a water harvesting system. Through multiple cycles, I noticed that the mass changes were not only extremely fast, but also very repeatable. This is due to rapid sorption kinetics and aluminum oxide bonds, which prevent its hydrolysis. Since the water harvesting cycles could be repeated every 35 minutes, numerous cycles could take place in one day. The following graph demonstrates the projected amount of water that could be harvested from 1 kilogram of moth over the course of 24 hours. These numbers can range from 1.8 liters all the way to 7 liters, depending on humidity levels. These numbers may, of course, vary in real-world situations due to external factors, but my results were 38% higher than previous literature due to the fact that their moth was only able to complete one cycle in 160 minutes. I also investigated novel ways on how best to arrange the moth to allow for maximum absorption. First, I arranged the moth in a thin, even circular spread. Second, I placed the moth on an oscillating shaker to allow all sides to access ambient air. And finally, I placed the moth in a standard mound. The moth did best in the thin circular spread owing to its great surface area, estimated to harvest 27% more water than the standard mound. Both performed better than the dynamic test. Finally, I designed a simple and very low-cost moth-based water harvesting system using parts that could be accessed on Amazon or 3D printed. To operate the harvester, you first place the moth inside of a 3D printed chamber. During the absorption phase, the chamber remains open to give the moth exposure to the air. In the desorption phase, the lid is closed and the moth is heated to 45 degrees Celsius. When heated, the trapped water molecules are released back into the air, which are then blown into a tube into a cooled insulated box where they will condense into water. After testing the 3D printed chamber, I found that the moth in the chamber functioned similarly to how it functioned in the glove box setup used previously. In conclusion, this research successfully synthesized moths and applied them for the purpose of atmospheric water harvesting. In the future, I would like to test moths and the water harvester on a much larger scale. It is important to further explore these materials as they may provide a much needed potential to provide water for many. Thank you.
Thank you, Caitlin. I wish you success in scaling this apparatus up to get more water. Thank you very much.
Thank you.
Our next speaker is Lucy Lee. She is a junior at Greenwich High School and took 4th place in life sciences for footprint reduction of PET fiber waste in refuse environments via non-toxic Ideonella salconensis degradation. I'm going to let her talk about that. Take it away, Lucy.
Okay. Hi, my name is Lucy Lee. I am a junior at Greenwich High School, and my project was the footprint reduction of PET fiber waste in refuse environments via non-toxic Legionella sacchensis degradation. So the accumulation of clothes in the environment is definitely a growing problem, especially with the rise in popularity of fast fashion. More and more clothes are being discarded in landfills, and when synthetic materials like polyester or PET fibers are discarded in these landfills, they can spend up to centuries here because they're not biodegradable and they spread infectious diseases and toxic compounds that harm plants and animal life. So to address this issue, I wanted to find a method that lessened PET fiber waste contamination at its source. So my research investigated the degradation capabilities of the bacterium Legionella sacchensis, or ESOC for short, which exhibits the highest natural PET degradation efficiency and thwarts any potential ecological issues that can be caused by toxicity in alternative methods like chemical recycling. So what is this Legionella sacchensis? It was a bacterium discovered in 2016, and scientists in Japan found that this aerobic bacterium could degrade PET into its constituents ethylene glycol and terephthalic acid, or EG and TPA for short. And with this knowledge, I hypothesized that due to the aerobic nature of ESOC, this bacteria can grow and thrive in moist aerated soil, and I could therefore push its degradation capabilities onto PET fibers in soil on the ground. So to test this, I made varying plate configurations with different soil concentrations and an R2A nutrient agar medium. And when this configuration was complete, I had added 100% PET string onto the surface. But before this experimentation could begin, I wanted to evaluate ESOC's growth on PET in soil without the presence of a fiber surface. So to test its growth, I took a method from Dr. Colin Charnock, where he tested ESOC degradation on plates of just nutrient agar and PET agar, whereas in my experiments, I had added soil and I had made an amorphous PET agar layer for the bacteria to degrade, and I call this condition like plate C as a control. And to grow this ESOC, I put it in a broth, and I had inoculated it with a sterile pipette onto plates and shook them to spread it evenly. So during the observation, during my experimentation, I had used a light microscope to observe growth and bacterial health, and to provide information on the surface microstructure, I took samples and dried them overnight, and then I analyzed them with an SEM machine, scanning electron microscopy. So what really stood out to me was that at 3 weeks of plate C, I identified the bacteria growth, which is seen in the image here. The bacteria is circular and it grows really concentrated. And seeing that that bacteria does indeed grow in soil, I used configurations 2, 3, and 4 to really push the degradation capabilities of ESOC. And on plate 2, you can see that the ESOC has appendages that have attached to the string. And with this, I saw this as visual evidence that the bacteria does indeed attack PET fibers. And as you can see on the image on the bottom, the growth is concentrated on the string, as you can see by the little white dots, and there's a very visible gap in between, which shows that the bacteria did indeed eat away at the fibers. So then I used other plates, 3, 4, and 5, to further it on to the string. And what was really beautiful as I was doing observations is that you can see there's a very obvious and visible concavity on the string with lots of growth concentrated at the tearing sites. And this was visual confirmation that in soil, with the help of a nutrient agar, the bacteria Legionella sacchensis can degrade these fibers. So after this visual confirmation, I washed these strings via ultrasonic bath, and I decided to determine the weight loss analytically. So I compared untreated PET with treated PET by comparing the initial and final mass. In these graphs below, on the left graph, the x-axis shows different plate configurations, and on the right, the x-axis shows different soil configurations, and the y-axis is the mass of PET string lost. And as you can see, for a 50% soil configuration, the PET lost was the most. And to further characterize this PET loss, I found the change in linear string density. As soil concentrations increased, the change in linear string density trended linearly from clear PET string, and the change in linear string density had also increased. But since my fourth plate didn't actually yield the highest PET mass loss, this data suggests that PET degradation is less uniform in higher soil concentrations, which is a potential drawback of using higher concentrations in soil. So overall, in the duration of this research, I found that the degradation capability of the bacteria ESOC is in fact applicable to 100% PET string in a soil environment with the aid of an R2A nutrient. And of the samples of string cultivated in soil, plates with a 50% concentration yielded the highest amount of PET loss at 13% decrease in mass over a period of just 3 weeks. Both the visual and quantitative results from this research demonstrate that ESOC degradation, demonstrate the degradation of PET string via Edenalis achiensis, and it highlights the potential of this bacteria to provide a non-toxic degradation method of PET fibers and waste refuse environments. Thank you.
Thank you. Thank you. With all our fast fashion being basically disposable, that would be a good technology to use. I call it my son's socks, e-socks, when I find them in the duffel bag. Our next speaker is Bridget Haddon. She is a eighth grader at Central Middle School, and she's going to be talking to us about contamination in Long Island Sound. Bridget? I should also say that Bridget has won many awards. First place in physical science in 8th grade. She even won money. And second place in Petite Family Foundation Women in Science and Engineering Award. She was nominated to compete in the Thermo Fisher Scientific Junior Innovators Challenge as well, and received the Society of Women's Engineer Award, Hartford section.
Hi, so for my presentation, it's titled Demonstrating the Persistence of Long Island Sound Polyaromatic Hydrocarbon Contamination via Stormwater Drainage Location. So polycyclic aromatic hydrocarbons, also known as PAHs, are organic compounds that consist of 2 or more aromatic rings. As you can see from the diagram here, PAHs can often be found as a result of urban stormwater runoff, as a result from motor vehicle usage, oil spillage, vehicle tire wear, and asphalt road surface materials. As such, individuals are often exposed to PAHs in their daily lives, ubiquitously in the air, foods, and water from stormwater. pH-contaminated stormwater runoff has led to an accumulation of these pollutants in other bodies of water, such as rivers, streams, and lakes, further impacting water quality and associated pollution. When in contact with marine organisms, PAHs can have toxic effects. PAHs are absorbed, transported, and exposed to various organisms through microplastics, another concerning environmental conflict in aquatic ecosystems. These PAHs have been found in many parts of the Long Island Sound. The drainage located near the Long Island Sound contributes to the amount of PAHs found in the Sound. The goal of my project was to characterize the persistence of PAHs in Long Island Sound water as a function of temperature, water movement, and location relative to stormwater drainage. So for this project, I focused on phenanthrene and naphthalene because they're both many times found in pHs. For testing the sample, so I went to Long Island Sound and got 9 water samples, and to test these samples, I used a fluorescence spectroscopy. I was using a fluorescence spectroscopy because both phenanthrene and naphthalene are very fluorescent and would be easily detectable. These graphs show how phenanthrene has a 235 nanometer excitation level and a 360 nanometer emission level. Naphthalene has a 210 nanometer excitation level and a 320 nanometer emission level. These bottom 4 graphs show the emission calibrations of both naphthalene and phenanthrene. As I previously mentioned, I went to Todd's Point in Greenwich to take 9 water samples. The first time I went, it was September, and I made sure to track where I got these 9 samples from. The red dots on the first image show where each sample is taken. I also decided to learn a little about the currents near Long Island Sound or near Todd's Point because I thought this might be important when knowing how currents affect the amount of pHs found. Next, I used a luminescence spectrometer. The emissions were recorded on this machine. I converted these emissions to the concentration of each pH. They are separated by each location, and then each graph shows the water at a different temperature. I focused on 3 different relationships towards the water: facing, facing away, and protected locations. Each seemed pretty consistent with temperature and with the other similar samples. For example, samples 4, 5, 6, and 7 were all the samples that faced the stormwater release, and in both the phenanthrene and naphthalene graphs, they trended up with each warmer temperature. Most of the samples in general tended to trend up with the warmer temperatures, and much of this is most likely due to the fact that humans are at the beach more often with warmer temperatures. The reason why naphthalene is so much higher than phenanthrene in these graphs is because it has a higher solubility in water. Oh, and in this one, it shows how overall the areas facing the stormwater releases are most affected by pHs. After closely examining phenanthrene and naphthalene at these 9 locations on 3 different days with different temperatures, I've noticed excellent agreement between the locations tested and the relative amount of pH found. This graph shows the location-to-location agreement between phenanthrene and naphthalene at 70 degrees. This figure shows how still locations, for example, locations that are blocked from the flow of water or is minimized, have a lot of pH. These are the locations where water tends to sit. In conclusion, pHs are being found in many bodies of water and are affecting many species' lives. This research characterized the persistence of pHs in the Long Island Sound coastline. I took water samples from areas by Todd's Point. These samples varied relative to coastline water runoff and currents at 3 different temperatures. The most pHs were found in the 70 degrees water rather than the 40 or 55 degrees. So Long Island Sound pH content from stormwater runoff increases the temperature, appears to move freely with currents, but collects in inlet areas with reduced water flow. For future work, I would like to take more water samples of different parts along the Long Island Sound as a function of weather. Thank you.
I'm happy you are going to high school, so you have a few more years to work on this local water body. Thank you very much. Our next speaker is Hannah DeCruz. Hannah won first place in the Environmental Sciences Award with Connecticut Association of Conservation and Inland Wetlands Commissions. Hannah, would you like to take it away here? She is an 8th grader at Eastern Middle School. Yes, we see you.
Okay.
We see your
Hi,
presentation.
my name is Hannah. Sorry?
Yes, we see your presentation.
My name is Hannah DeCruz, and I'm an 8th grader at Eastern Middle School, and my project is the implementation of rhizobia nitrogen fixation to increase overall crop production and inhibit fusarium wilt. So even though 70% of the air is made up of nitrogen, plants find it really difficult to absorb this element in its natural form, and regular fertilizers and pesticides to increase crop growth have a really bad impact on the environment, causing things such as runoff and toxic algal blooms. To feed a growing global population, new methods to increase crop production and inhibit the wilting effects of plant pathogens is becoming more and more essential. Nitrogen fixation is mediated by bacteria, specifically rhizobia in this experiment, and it represents a more favorable approach to providing nitrogen to plants. So here's a little model of how it works. So the nitrogen in the air is turned into fixed nitrogen, which the plant can absorb more easily. So this research project investigated improvements in plant growth for soybean through the addition of nitrogen-fixing bacteria, or rhizobium, for healthy plants, as well as those afflicted with Fusarium verticillium, and compared to similar growth studies for urea fertilizers. And here's a little example of what Fusarium on an actual plant would look like. So for these experiments, I placed a single soybean seed in a 2-inch pot with permafused soil for both my configurations to create the normally grown control setting. And for those with N bacteria, I pre-soaked the seeds in N-rhizobium inoculant before planting, and I planted 69 milligrams of urea to each 2-inch 1-cm planting to create the fertilizer added plantings. Configuration 2 contained plantings similar to those in configuration 1. However, 2 grams per liter of Fusarium verticillium was added to the planting soil prior to the addition of the soybean seeds. For each soil configuration, plants were watered every single day with deionized water, with 12 hours of artificial lighting, which lasted from 7 a.m. to 7 p.m. in a 68-degree horticulture lab. Plant height was measured each day for a period of 1 month to trend growth for each configuration. So here's some pictures of my plants throughout their growing stages. So in figure 3.1, you can see their front view when they first started to grow out. And in figures 3.2 to 3.3, you can see when they're in the middle of their growing stages, when they're a little bit taller. And then in figure 3.4 is when they finally finish growing. So these graphs show the results of the healthy soybean seeds. Figure 4 shows healthy soybean growth compared to the urea fertilizer and nitrogen bacteria, with the x-axis representing days and the y-axis representing the plant growth in centimeters. Figure 5 depicts the 4 different plants and their height in centimeters, and figure 6 shows the plants and their growth rate with centimeters per day. And the results from these graphs highlight that the addition of N bacteria to healthy soybean plants increases their height by around 25% and their growth rate by around 15%. As a comparison, the direct addition of fertilizer increases soybean plant height by around 44%, with the growth rate increase of 34%. So these are my graphs for the Fusarium infected plants, and these graphs have the same variables, but these are the plants infected with Fusarium. And the results from these graphs highlight that the addition of that the infection of soybean with Fusarium causes the anticipated plant wilt, with a 19% decrease in plant height, which you can see in figure 8, and a 15% decrease in plant growth rate. And regarding plant height, Fusarium with N bacteria grew to 15.5 centimeters in 25 days, which is 45% higher than Fusarium soybean and 17.4% higher than the healthy soybean. And regarding the plant growth rate, Fusarium with N bacteria grew at around 0.65 centimeters per day, which is 44% higher than Fusarium soybean and 22.6% higher than the healthy soybean. So in order to evaluate the nitrogen content in the leaves of each soybean growth condition, the near-infrared reflectance spectrum, which ranged from around 1,000 to 2,500 nanometers, was measured for the plants below. And the NIR spectra are illustrated in figure 10. And from those, the NDNI is calculated for each growth condition based on reflectance at 1510 nanometers and 1680 nanometers for each. And an increased NDNI content indicates a higher nitrogen content, with the normal range falling from between 0.02 to 0.1. And as expected, the addition of N bacteria to healthy soybean increases NDNI by around 32%. Another way used to further evaluate the nitrogen content of each growth condition was electron microscopy, or SEM, along with energy dispersive spectroscopy, or EDS. And sample SEMs of the soybean leaves are depicted in figures 12 through 13, and the corresponding EDS spectra for each growth condition are in figures 14 through 19 below, and were collected via spot analysis at each soybean leaf's upper surface, which is the crosshair figure in figure 13. And the analysis highlights a 26.6% increase in nitrogen carbon for N bacteria growth, but the urea plants were unchanged. So overall, in conclusion, the fertilizer increased growth rate by around 34% and plant height by around 44% in normal plants, and the rhizobia increases plant height by around 25%, growth rate by 15%, and regarding its growth for Fusarium, it grew around 0.65 centimeters per day, which is 44% higher than Fusarium soybean and 22.6% higher than healthy soybean. So even though the fertilizer has proven to be more efficient than the bacteria, implementing large amounts of nitrogen into the soil for industrial use may cause a negative impact on the environment. And the rhizobia was able to grow a healthy soil plant without any harmful impacts towards the environment, even though it was slightly less efficient than the fertilizer. Weighing the overall benefits of both enhancements of the soil, the rhizobia appears to be a better alternative compared to the traditional fertilizers, as it is less damaging to the environment but still improves growth. My next steps for this research would explore alternative methods to make urea fertilizer more applicable and beneficial to the environment, or enhance the efficiency of nitrogen-fixing bacteria. Thank you.
Wow, thank you, Hannah. That's just so interesting. Thank you for presenting. Our next speaker is Amelia Fowle. She is an 8th grader from Central Middle School, and she placed second in the 8th grade life sciences and won the U.S. Metric Association Award and was nominated to compete in the Thermo Fisher Scientific Junior Innovators Challenge. And we are excited to hear your presentation, Amelia.
Thank you. I just need to share my screen. Can you see my screen?
Yes, we can.
Okay, so hi, I'm Amelia Fell, and my project was on reducing food waste with the early visual detection of bread mold using BODIPI colorimetric card detection of 1-octane-3-ol. So there's a big problem in the US where we waste lots of food, but it's clearly preventable. Bread is a staple of a typical diet, yet much of it is often wasted once the mold is seen. But the fungus can begin to grow in areas that are not immediately visible through the packaging, causing consumers to eat harmful moldy bread. My project seeks to devise a card sensor that tells you if the bread has gone bad before the sell-by date, so don't buy it, or it's okay to eat after the expiry date, which helps prevent waste. With a focus on black mold, which commonly grows on spoiled bread, my sensor will change color from pink to salmon white as soon as it detects 1-octane-3-ol. I identified the most significant volatile organic compounds from black mold in low and high preservative breads. However, I learned that the low preservative ones grew moldy too quickly for testing. So I ran 400 microliters of headspace gas for each bread using gas chromatography flame ionization detection, which I compared with a 0.5% 1-octane-3-ol standard in ethanol, where the highest peak at about 6.5 minutes was identified as 1-octane-3-ol, which was the most prominent VOC. It became my fungal analyte of choice because, according to Lynn et al., it provided the most sensitive detection to bread mold growth. I took that same 0.5% solution and put 0.1 to 2 microliter injections into the gas chromatogram, which was then analyzed by GCFID, and the corresponding peak areas at 6.5 minutes were measured. I plotted the 1-octane-3-ol mass to peak area to create a best fit calibration line. Then I used scanning electron microscopy analysis to characterize the bread mold growth stages to better understand the mechanism of VOC emission. I took samples of bread mold since day 1 of the green mold growth with SEM, and it highlighted the presence of the different parts of bread mold. In the yellow stage, the mold was getting more aggressive, and in the black stage, the fungus was literally covering everything. And this showed the progressive growth of bread mold as the extensive spore content increases, which also supports the measurable increase of 1-octane-3-ol in VOC emission. From this, I concluded that 1-octane-3-ol emitted before visible mold growth. To provide evidence of this, I took high preservative bread slices and withdrew 500 microliters of headspace gas every day. I analyzed them with GCFID to find 1-octane-3-ol. In 5 days, there was nothing. In 8 days, a 1-octane-3-ol emission was identified, but the fungus wasn't fully visible until 21 days. In Table 2, it shows gas coming off the bread long before it could be seen, which matches the SEM data and highlights 1-octane-3-ol's pre-visual emission. In Figure 9, the mold starts to grow after about 13 days, then really takes off. The pink area is where it's visible, and the blue area is where my sensor needs to detect the fungus that we can't yet see. So how do I detect this? There's a green dye called BODIPI that's specific to 1-octane-3-ol. I provided evidence of this with a Fourier transform infrared spectrometer. First, I added 100 microliters of 0.5% 1-octane-3-ol to some of the BODIPI solution. Then I mixed the two in ethanol, where some bonds formed and broke. Despite BF bonds breaking, double CO and BC bonds formed, which implies that BODP is selective to 1-octene-3-ol. And this is how I envisioned and constructed my sensor. I dried BODP on a cotton piece, then added a few drops of liquid 1-octene-3-ol, causing a 530 nanometer emission. So the green only got brighter, which is not noticeable enough for a color change. Then I mixed BODP with an orange dye called rhodamine 6G in a fluorescence resonance energy transfer system in a 4:1 ratio. Although there was an orange color change when rhodamine had a 570 emission when the two dyes were in close proximity, when they were far apart, BODP worked by itself and rhodamine was left alone. In number 4, the green and red emissions got brighter, where the color turned from pink to salmon white, which is more visible than the green to brighter green. But since my sensor had to detect the fungal gases, I exposed it to 1-octene-3-ol gas. I did this by putting 1 microliter of 1-octene-3-ol liquid into various dice bottles with my sensor, where they were heated to 30 degrees Celsius in a GC oven. The results were then compared with clean, liquid, and unused sensors, which are here pictured with smartphone in room lighting, although there's a more noticeable difference in UV lighting. But smartphone imagery was needed to ensure the difference between the two lightings. So I analyzed the spectra of the gas-exposed sensors with a fluorometer, which showed progressive change in sensor color with increasing gas exposure. But I needed to characterize the color change without a fluorometer. So I used various fluorescent intensities to create a color code model where the values resulted in a linear curve, allowing me to predict concentrations. Spectrometers are rather inconvenient, however, so I decided to use smartphone imagery with RGB values, which is more consumer friendly. It's the same color code model as a spectrometer, but with a better correlation efficient, where the sensor color equals red times green minus blue divided by 100. And in the future, I'm hoping to program an app where the consumer takes a photo of my sensor on the bread, and the app uses my algorithm to identify RGB values and predict fungal concentrations. If there's any mold, don't eat the bread and throw it away, regardless of the sell-by date. Overall, I've created a color-changing sensor that, combined with smartphone technology, can determine if a loaf of bread is good before or after the sell-by date.
That is impressive, Amelia. Thank you so much. And now I know, it's kind of scary to think what's in the bread. You can't even see it. Our next speaker is Zara Hawk. Zara is a sophomore at Greenwich High School, and she was on the first Selectmen's Youth Commission and received first place in future sustainability and an invitation to this year's National Genius Competition. Please share your screen, Zara. Thank you.
Sorry, I was muted. Hi, so I'm Zara, and I'm a sophomore at Greenwich High School. And today I'll be talking about my project, which is entitled Development of an Efficient and Easily Applicable Low Energy Process for the Degradation of PFAS. So PFAS are also known as forever chemicals, and they are called this both for their prevalence in our environment and our drinking water, and also for the dangers associated with them. PFAS are suspected carcinogens, they adversely affect reproduction, and more recently there have been studies released that even suggest that they may have negative impacts on antibody production, which is concerning given the current pandemic. Additionally, PFAS are incredibly widespread. They're found in everything from household items like wax paper and nonstick cooking pans to even flame retardants, which is particularly concerning given the forest fires going on in Canada right now. So my project aimed to develop an efficient, easily applicable, and low energy process for the degradation of PFAS. Currently, in the status quo, PFAS are filtered out of our drinking water and then sent to incineration plants, in which they are incinerated at incredibly high temperatures, which takes obviously a lot of energy and also a lot of time. The other thing about this incineration is that it's been found to be kind of ineffective. A lot of times, once those PFAS are incinerated, they're simply re-released into the air from those incineration facilities, which is not helpfully contributing to solving this problem. So in order to do this, I essentially mixed PFAS with sodium hydroxide, water, and a small amount of DMSO. And this resulted in kind of a two-phase degradation of PFA. So first, PFOA, which is the specific PFA that I chose to study, PFOA is a type of PFA that is very prevalent in Connecticut, was decarboxylized using this sodium hydroxide. And the products of this reaction were this long carbon fluorine chain, which is the remnant of the PFOA, and sodium carbonate. Sodium carbonate is generally regarded as safe by the FDA and is also found as a component of various detergents and cleaners, as well as a food additive and an inert ingredient in pesticides. So it's really kind of a much less dangerous thing than PFOA. However, this remaining chain is unusable and not really much better than PFOA itself. And so I decided to continue breaking down this chain via thermolysis. And so the thermolysis of this remaining chain resulted in 4 different types of light fluorinated carbon compounds. And these 4 different light fluorinated carbon compounds all have different uses that they can be kind of repurposed for, including as a blend component in commercial air conditioning and fridge systems, as a fire extinguishing agent, or even as a propellant in pharmaceutical devices. And overall, this process of decarboxylation plus thermolysis takes about anywhere between 10 and 12 hours, and the reaction does peak at around 4 hours. So it's much more efficient. And it also happens at 120 degrees Celsius, which is a much lower temperature than incineration. So I did accomplish my goals of a low energy process as well as a quicker process. This process is also effective. I effectively broke PFOA down into sodium carbonate and 4 light fluorinated carbon compounds, which can be easily repurposed, which is something that incineration just does not accomplish. Thank you for your time, and that was my project.
That is amazing. I think maybe you could save the world with that project. Very impressive. Yeah, the PFAS, we call them PFAS in our group, and they are a huge danger. And I think you were telling us how many different ones there are. There are thousands of them, and correct? And you zeroed in on this one that's particularly common in our area.
And actually PFOA, recently the FDA, the EPA, changed their advisory on PFOA from in 2016, it was 70 parts per trillion, and now in 2022, it's 0.004 parts per trillion. So that kind of underscores how deadly they really are.
Well, hopefully we'll have some time to talk about this a bit more as we go forward toward the end of the program. Thank you, Zara. Our next speaker is Naomi Park. She is a junior at GHS, and she took first place in engineering, 3rd place in applied technologies, a 3rd place in physical sciences, and the Office of Naval Research Award and the Stockholm Junior Water Prize state nomination for her presentation. Take it away, Naomi.
Yeah, thank you for the introduction. So yeah, my name is Naomi Park. I'm a junior from Greenwich High School, and I'm really excited just to tell you a little bit about my research. So my research is entitled Concurrent Removal of Rising Soluble Ocean Carbon Dioxide and Oil and Water Contaminants via Multifunctional Remediation Framework. So briefly, just to kind of lay out the problem here, today there are 3 detrimental pollutants that continue to attack our world's oceans with really limited ways on how to solve them. And so one is carbon dioxide. And when we generally think about CO2 emissions, we think of its effects in the atmosphere. However, what many fail to realize is that as the concentration of CO2 increases, our oceans absorb more and more of this CO2, leading to ocean acidification, which directly harms the growth and survival of entire coral reefs and ecosystems. 2 are crude oil spills. And so every year, 1.3 million gallons of toxic crude oil are spilled into oceans every year. And current remediation methods, the one I have on the screen, such as oil booms, only remove visible surface contamination, basically leaving behind this invisible soluble oil that continues to spread and contaminate even more water. And then 3, hold on, I think this is like acting a little weird, but okay. And then 3 is plastic pollution, in particular styrofoam waste. And so in search of a solution, I came across these things called hypercrosslink polymers, otherwise known as HCPs. And essentially, HCPs are these non-polar materials that have a really high porosity and surface area. and therefore have been used in previous environmental remediation studies to capture and remove pollutants. However, there are many shortcomings with current HCPs. One is that traditional HCP synthesis often requires use of a lot of costly reagents and methods, but recent literature by Dong et al. Actually demonstrates the development of a cost-effective method by using styrofoam waste. Now, even with this innovation, why HCPs remain so stagnant in literature, even though they have these really great capabilities, is because of implementation. Today, HCPs only resemble this insoluble powder. So I don't think we can expect to throw powder into the ocean and then hope for the best. And so therefore, after finding this out, I really saw utilizing these HCPs as an opportunity and thought to myself, if I could create a way to create more of a stable and implementable system where this framework could essentially be left indefinitely in water, it would be able to potentially remediate some of the most detrimental non-polar pollutants from seawater. As such, my research focused on the design and creation of a multifunctional remediation framework I call MFRF to effectively remediate both the soluble oil and carbon dioxide pollutants in water while concurrently lowering the ecological footprint of styrofoam waste. Now, there's a lot of my poster is definitely very dense, so I'll just briefly talk about the different components of the device that I settled on. So in my device, it's essentially three main components. First, I have a melamine foam to act as the base. And why I chose melamine is it's because it's been used in a lot of previous environmental literature. As one, it's just a very cheap and plentiful resource. And secondly, it's actually very robust in nature and able to withstand harsh environmental conditions like wind and ocean waves. Secondly, I used a PTFE dispersion to act as the binding agent. And why I chose PTFE was because, again, in previous literature, it's been used to bind non-polar materials together, specifically in fuel cells. So I thought that would be a good binding agent. And then finally, I have the HCPs I synthesized for pollutant removal and capture. So my results indicate that not only does the MFRF exhibit this effective remediation in separate contaminated solutions of the soluble oil and CO2, but also has this novel ability to remove multiple contaminants simultaneously. And so the device has a multitude of implementation possibilities, such as complementing traditional oil spill recovery methods, such as oil booms, or being simply implemented at the shoreline via tethering or at deep sea depths using a buoy. And I envision this method for less aggressive oil or CO2 remediation. And then finally, I'll just talk a little bit about where I hope to go with this project in the future. So I was actually lucky enough to qualify for the Regeneron International Science and Engineering Fair, where I competed just this past May in Dallas, Texas. And there I was, it was really cool. I was a recipient of the Patrick H. Hurd Award for Sustainability given by the EPA. And so I'll have the opportunity to present my research in DC at their Sustainability Expo. And I think that just the EPA's attention to this issue and my project really points to how significant of an issue and prevalent of a problem it is. And it also really gives me hope about the future, as there are many organizations like the EPA that care about giving opportunities to students who are passionate about environmental science and really want to make effective change. So yeah, thank you so much.
Thank you so much, Naomi. MFRF, make it a hashtag. There we go. Thank you. Our next speaker is Sarah Rahimtullah. She is an 8th grader at Central Middle School, and she will be talking to us about our desire for convenient spring water causing at the expense of meaningful microplastic harm. She won the first place at the Energize CT Future Sustainability Awards and the Freeman Family Excellence in Chemistry Award. Go ahead, Sarah, and tell us about your project.
Okay. Hi, I'm Sarah. My project is titled Does Our Desire for Convenience Spring Water Come at an Expense for Meaningful Microplastic Harm? So, the average American consumes around 74 to 124,000 microplastics per year, the way that this diagram shows, which includes eating seafood or just breathing it through the air. However, my project focuses specifically on bottled water. Bottled water can add a total of 90,000 microplastics to that base number, which has a really negative impact on human health. So, as shown in this next diagram, consequences include skin problems, lung cancer, respiratory issues. But since my project involves the drinking of bottled water by mouth, my project targets the reduction of digestion issues and gastrointestinal diseases. However, bottled water is a necessity that many are unwilling or unable to give up, whether for convenience or in areas where there's a lack of access to natural clean drinking or tap water. So the objectives of my project were to evaluate the number of microplastics in the following popular water bottle brands, which include Aquafina, Poland Spring, Lightwater, Fiji, Voss, and Kirkland, which is Costco's brand of purified water per 16 ounces. So I can estimate the human consumption and microplastic harm and find which bottled water brands are healthiest and reduce microplastic levels found in humans. So my first step was water sample preparation. I poured 3 bottles of bottled water each to the metal pour water filtration system. The water was vacuumed down through by the faucet aspiration system, but all the microplastics settled on the 5UM mesh screen filter, which I used an eighth of to examine under the SEM. Okay, so the next part is SEM, which was scanning electron microscopy, and EDS, energy dispersion spectroscopy. So I used the SEM to look at my filters under a microscope, and after a while, I started to kind of recognize what a typical microplastic looked like under the microscope. I was able to zoom in on the images to identify any visible debris and could use the EDS to verify the suspected microplastic's identity by looking for high levels of carbon, not iron, which is what the filter was primarily made of. Okay, so down here I have what the metal grid looks like on the right and the corresponding EDS graph on the left, which showed high levels of iron. So like these two here are iron. And then as well as chromium, which are like these two, and then nickel, which is like these. So those are like a sign of the filter, and that's what the filter was made out of. So it accurately reflects what the filter was made out of. But down here, I have a plastic, as shown here on the right. So that's what a typical microplastic would look like, and the corresponding graph here on the left, where you can see very little iron, but a really high peak in carbon, which is like this one. Which is what this plastic, the microplastic, is primarily made of. So I know that it's a microplastic, and then I should add it to my total count. Okay, so down here I have a few more photos of plastics I captured from my samples that I thought might be interesting to show, like a few of the microplastics that end up in the water we drink. Because a common misconception about microplastics is that they're all like perfect spheres. So the two on the left look more like the ordinary microplastics that I coincidentally found right next to each other, and the other is an odd-shaped plastic from Poland Spring. So my data is up here. So these are my results when I totaled everything. So on the left, I have brand of water, and then on the right, corresponding microplastic content. So I had Aquafina with 48, Poland Spring with 128, Kirkland's Purified Water with 96, Life Water with 40, Fiji with 50, and Voss with 64. So as I've said, Poland Spring has the most microplastics with 128, which is over triple 40, which represents the levels found in Life Water. So the average number of plastics per bottle was 71. And one of the things that I noticed was that the water bottles that had less water in them ended up having more microplastics per 16 ounces. And this kind of leads me into my next point, which is about the caps. So I noticed that the bottles that screwed with like less sturdy caps, so that would be like Poland Spring or Kirkland's Purified Water, they had higher levels of microplastics than those that had sturdier caps like Voss or didn't screw at all like Life Water. So to fully grasp the magnitude of my project, I converted all my numbers to microplastic consumption per year, which is what this bar graph on the right represents. So this is assuming a person lives off 48 ounces of solely bottled water from that brand a day, like they would if they lived somewhere where they had a lack of access to natural clean drinking water. So for Life Water, they would be consuming 120 microplastics per day and 43,800 microplastics per year. So that number might not sound great, but for Poland Spring bottled water, they would be consuming 384 microplastics per year and 140,160 per year. So in conclusion, going with a bottle like Life Water could save you from consuming up to 96,360 microplastics per year. And it'd be far more healthy for you, much lowering the risk of gastrointestinal diseases and digestive issues. So done here, I have future work. I want to keep studying microplastic content in other bottled water, as well as studying the additional ways that humans can consume microplastics. I also want to study the source of microplastics in bottled water and see if I can find ways to reduce the dependency on bottled water. So that's it. Thank you.
Wow, thank you, Sarah. How many bits of microplastics would you have to have together to be able to see them with the human eye? Do you know? Like, if you
I'm not totally sure, but I think for the most part, like you can't really see them with the human eye.
yeah, yeah. But if I understood you right, the bigger the bottle and the difference of the cap determines, you think, what the amount of microplastics in the water, if I got it right.
Yeah, well, I'm not totally sure yet, but
Mhm.
what I wanted to look into was to see if all the microplastics come from the cap. So if they came from the cap, like when you're screwing it, and if it comes from stuff like that, then that would probably be why like having a bigger bottle with like a same size cap would have less microplastics, like
Right, right.
proportionally.
Ah, very interesting. Thank you. Thank you very much. Our next speaker is Kate Wick. She is an 8th grader at Central Middle School, and she received 5th place at the Axion Biotechnology Conference, I guess, and a U.S. Metric Association Award, and Connecticut Science Supervisors Association Award. Take it away, Kate.
Hi, I'm Kate Wick, and I can't wait to tell you about my project, which I call Wavelength-Specific Illumination of Hydroponic Growth Systems for Increased Crop Production. In our world today, water scarcity has become a daunting reality for many countries around the world, such as Lebanon, Pakistan, Syria, and many more. These communities often suffer from inadequate sanitation and the spread of deadly diseases like cholera and typhoid fever. These seem like faraway problems that don't really affect us, especially in Greenwich. However, this mindset is dangerous because projections tell an entirely different story. The United States alone is predicted to have high water stress by as soon as 2040. And it's not to say people haven't attempted to stop it, as we're often told to turn off the faucets, take shorter showers, don't water the lawn, and things of that nature. And that's all fine to do, but the truth is, this alone is not going to have the impact that we're really looking for. That's because domestic water use only accounts for 10% of the total. It's simply not enough. The real cause is irrigation, for soil-based agriculture. Currently, this industry accounts for 70% of global freshwater use. And as time goes on, these levels can only be expected to increase if we hope to sustain a growing population. But it doesn't have to be this way. Hydroponic systems have proven to solve many of the problems with traditional farming by maximizing water use efficiency by 70 to 90%. But just because it's a positive step into the future doesn't mean that there aren't any areas of improvement or problems to be solved. One problem I noticed was that these hydroponic facilities tend to be prone to some sort of fungal presence, such as Fusarium verticillium, which is a fungus that causes plant wilting, decreased plant health, and eventual death of crops. These types of fungi are a major threat to hydroponic systems everywhere, potentially inhibiting a future of sustainable food production. So currently, these hydroponic facilities use white light in an attempt to more accurately replicate natural sunlight. However, in my research, I decided to take this in a bit of a different direction and find a potential alternative. The purpose of my research is to look into the impact of various wavelengths on hydroponic soybeans, with a final goal of determining a lighting plan that will optimize both plant growth as well as the resistance to the harmful fungi, hopefully contributing to a future of sustainable farming practices as well as food production. So to conduct my experiment, I grew various batches of soybeans under red, blue, yellow, and green illuminations. I also grew some with white light to act as a control group. Some of my plants were fed with normal water, while others were purposely infected with fusarium to see the results. I used plastic folders instead of monochromatic LEDs because a main selling point of my research was to provide an inexpensive and accessible alternative to the white light, which meant no expensive LED lighting. Over the coming weeks, I collected data on the plants. I noticed that the regular plants without fusarium grew overall more than the infected plants, which was pretty much expected. The more interesting conclusion that I drew was that in the case of the red and yellow light, the color-specific lighting was actually outgrowing the traditional white light methods, suggesting its potential advantages of increasing growth outcomes as well as the plant's ability to resist the Fusarium verticillium wilting fungi. So halfway through my research, I realized that plant heights are important, but perhaps a more telling factor in determining overall crop yield would actually be the biomass of each plant. So relative to the regular white light conditions, red showed to have a 22% increase in the mass, while yellow showed an 11% increase in terms of infected crop conditions. So the red lighting proved to increase the biomass of the hydroponic soybeans by, again, 22%, which demonstrated a consistent impact across both the regular and the fusarium infected soybeans. Evidently, the data trends between height and biomass were quite similar in the proportionality between the color of lighting, only further reinforcing the promising outcomes of red and yellow light on hydroponic crop growth. So in the end, it became clear to me that agriculture is a very impactful and vital industry for our growing world. And that's why I wanted to make my research an alternative that would be effective, but also inexpensive and accessible, unlocking the potential of hydroponics and giving farmers the tools they need to pave a brighter future of healthy and sustainable food production. I hope you find this topic intriguing, and I hope we will continue to explore more sustainable practices in Greenwich and the world. Thanks for listening.
Thank you, Kate. That was great. I wanted to ask if so it's a shorter, it depends on the length of the light wave, the mass of the soybeans.
Yeah, so I noticed that the red and yellow light more specifically actually increased both the biomass and the height of the hydroponic soybeans when compared to just the regular white light conditions.
Mm-hmm. Very good. I think that those are our participants for this evening. I'll hand it over to Sarah, but I wanted to, so that we can take questions, but I wanted to make the comment that these students are a testimony to the high quality of education they're receiving and our public school system. And I really, really appreciate them being here tonight. Sarah?
Thanks, Myra. Myra, I lost connection with my computer, so I may need you to pick it up for a second, but I just wanted to say that listening to all these students, you used lab equipment, you worked with professionals, you grew things, and you looked at things around us with a different lens, and we are just so amazed by the work that you did. Really well done. Congratulations again on your achievements. We're just so proud of you. So if you're Myra, if you don't mind just taking over while I try to get back onto my computer, but students, if you could, panelists tonight, could you turn on your cameras again so we could continue with the two questions that we are moderating?
Yes. Well, of course, everyone wants to read about what you've done and see the recording, and it will be, it has been recorded and it will be posted so that you can access it again. I need to look at it again and really pay attention. A lot of this science is new to all of us. But there is a question whether or not we will be able to download these projects so as to view them more closely. What do you say about that, Cos Cob Library?
Hi, Myra. Sorry. We are recording the video for the presentation, and we will be able to post it shortly on YouTube. So you'll be able to see what they presented through the video.
Okay, very good. Very, very good. And another questioner is asking Sarah Hawk how her research on PFAS or PFAS can be scaled or have practical application. It sounds like she has that intention.
Yeah, should I answer that right now?
Please do.
Okay. So my dream for my research is to someday be able to implement it within water filtration facilities. So essentially that the PFAS will, like in the same building, go straight from being filtered out of water to being like destroyed and broken down. But currently, I think that the best implementation of my research would be in place of an incineration plant. So essentially, the PFAS would be taken to some sort of facility where my reaction or proposed mechanism would take place, and then the byproducts of that reaction, such as those small light fluorinated carbon compounds, would be collected and then could be resold to like refrigeration companies or air conditioning companies or something like that.
So it would be an entirely circular economy.
Yes, that is the vision.
Yeah, very good. You all used very high sophisticated equipment, spectrometers and electron microscopes. Where is all that equipment housed at your schools? Where do you get access?
So in our school, like our science program is like really, really resourceful, and like we're all so grateful for it. But there's like a room with all the lab equipment, SEMs, microscopes, and pipettes, and basically everything you need. And if there's something in the room that's like not there, like we order it, obviously if it isn't like too expensive, but within our budget.
Very good. It's good to know that that equipment is available to you as you are all putting it to very good use. We had, Sarah and I have devised a couple of questions that we wanted to open up to the panel. We wanted to ask you locally again, what effects of climate change are you already seeing, here in Greenwich, or feeling? What have you noticed just as a human being, a person? You could bring your science hat on too, but we would love to hear from you about that. I beg your pardon. Got noisy here.
Go ahead, Kate.
So I think that Greenwich has overall done a really amazing job in like preserving and maintaining the nature that surrounds us. Like while simply driving around our town during this time of year, I can see how beautiful everything is. However, as a resident, I have experienced the effects of climate change in various ways. So like coming from the perspective of like a gardener, the recent dry spells have proven to be a detriment to my plants that I plan to sprout and transfer to the garden this spring, and especially for my basil, which is now unfortunately deceased. Not to mention the grass on my lawn and many others lawns I was noticing became very brittle and lost kind of the vibrant green color that was there before. Although I wouldn't necessarily call this a drought, I have begun noticing like the increasing frequency and intensity of prolonged dry and unusually hot weather, which I think could potentially be an effect of climate change.
I'd also like to add, like, aside from the obvious like stuff that's going on right now with all the air and stuff, like climate has become like more erratic. Just today, like it was like, and yesterday especially, it was like kind of just hard to breathe. And overall, like there used to be a lot of animals around in my neighborhood to the point where it was like kind of an annoyance. Like there were turkeys, coyotes, and always every single year, many deer in my backyard. But this year, like they're all gone. And now I'm not like an expert in the animal control in our town, but I feel like it can be a result from like the changing climates and like just the general like instability and like inconsistencies of how it is, and over time like animals have been driven away from our neighborhood.
See, thanks, Kate. Does any other panelists want to comment on what they're noticing or feeling in terms of climate change here in Greenwich? I definitely, Lucy, agree. It's you know, when you see or don't see animals anymore, you start to wonder why and what's going on and where have they gone, and you may be connecting dots on, oh, well, maybe there aren't those trees anymore, or maybe we haven't had the right weather for them, or they're so yeah, those are all things that pick up. So kind of as you know, all of your projects are so, you know, your work and the projects that the research that you've done are so inspiring, but we want to know what inspires you and gives you hope about, you know, obviously there you addressed an issue, you identified an issue, you addressed it, you looked at ways to understand it more and maybe to solve part of that issue. But there's so many other issues, right? There's so many other problems, and we want to know what inspires you and gives you hope about what you're working on with these issues. Hannah, do you want to go?
Yeah. So what inspires me, really gives me about these issues, is seeing the motivation that a lot of other people have to care for our surrounding environment, such as the beach cleanup that was recently held at Todd's Point. It was just really eye-opening to see that many people get together and act upon an issue that we all care about.
Bridget, I saw your hand go up.
Yeah, kind of to add on to Hannah is that I think there's a lot of organizations, especially locally, that are working to solve many problems like climate change and things like that, and even smaller like the beach cleanups. And I think that's really nice because I feel like almost every weekend there's something for the community to do to benefit problems.
Kate, go ahead.
As I said before, just like in general, the beautiful landscapes of the Northeast are, I think, very well preserved in Greenwich overall. And I myself, I'm lucky enough to live across the street from a forest. And I think that the natural spaces like these are contributing to the health of the environment, but also for the residents, especially me, who enjoy hiking, swimming, and just exploring the outdoors. So this is one message that I think we all need to learn, is that the health of our earth and the health of the humans who are living on it kind of go hand in hand. And we'll often find that what's best for the planet ends up also being what's best for ourselves. So it really gives me hope to see how this land has remained untouched for so long, and I hope it can always stay this way.
Yeah, we definitely hope that we leave our home, our planet better than how we found it, right? For future generations. And that's what you are. You are our future generations. Hope it's better. Does anybody else have any thoughts on what inspires you and gives you hope?
I'll just pipe in to say that hope is kind of like a muscle. You have to use it, and it is an action verb, and it means that we have to take action, and not to have hope is just to kind of it's a cop-out. And I see hope in all of your work, because you are taking deliberate, sophisticated action in the face of big problems. And we appreciate you. And thank you very much for coming here tonight and presenting your work.
So I saw one more question in the chat. Do you want me to, it was this was another question about the microplastics in bottled water. And the question was, are there any other studies examining microplastics in bottled water?
Like I'm not so sure about that. I know it's definitely like a fairly new topic and like an issue because people had just kind of realized and like found microplastics in like human blood and like lungs. So there hasn't been like a lot of time for them to really find out. But that definitely like led to the topic as kind of like why was that? And then they found that bottled water was definitely a big cause. So there are definitely studies confirming that bottled water is much worse for you than like normal water from a filter. But I think that's like around it. Like I haven't been able to find any other studies.
Thanks, Sarah. I have a question for everybody. You know, again, there were so many different aspects of your projects and what you were using or who you worked with. Um, did you have a favorite part of your research project? Was there something that you just didn't expect to do and or something that you really enjoyed that you didn't think you would be exposed to? Hannah?
Well, I think the part I enjoyed the most of my project was just the experiment itself and the evaluation when I was like, evaluating my nitrogen content. It was my first time using those types of machines and getting to really go in depth with my research really excited me.
Yeah, it's same with Hannah. I thought it was like super fun, honestly, using the machines, and just like looking for evidence and stuff. It was like honestly like really mesmerizing because I had never used anything that saw anything so like small. It was like so microscopic, and I had never seen anything like that before, and it was just so enthralling.
All right, I saw Kate, Bridget, and then Zara.
Kind of like adding on to that, it was a really cool experience for me because I started off not really knowing anything about hydroponics, any of the machines I was working with. And then as I went, I kind of just gained more knowledge and experience and more understanding of just sustainability issues in general.
Yeah, so to add on, I think my favorite part was working with the luminescence spectrometer because like at the beginning I needed so much help and I didn't really understand how to use it, but because I tested 3 different sets of water samples, I had a lot of practice and it ended up being just a lot of fun and it was a lot of clicking of buttons and pouring water and yeah.
I think that like one of the best moments of research for me was definitely like my aha moment when I like saw my results and I realized that, you know, like my idea, my like proposed mechanism actually did work. And another like underrated moment of research, I think, is this doesn't necessarily have to do with the research, but seeing your poster printed kind of really pulls it all together and kind of makes me realize like, oh my gosh, like I really did this. And kind of on that topic, I think that our teacher, Mr. B, deserves a lot of credit for teaching us like so much. I've learned so much in this class, so much more than I'd learned in like a typical science class. And we really all owe a lot to him.
Well said, Zara. Well said. That was great. Well, do we have any other questions or Myra, do you have any other questions you want to ask before we wrap it up for
Well,
this
I
evening?
would just open it up to anybody who has a comment or anything else they want to share. It's so wonderful hearing from you. You know, we got the idea to do this because the world out here, you know, has very little contact with you. And we want to repair that. I mean, unless we have, you know, students that do this kind of work as children, or if we were teachers ourselves, we just don't have this kind of opportunity to learn about what you're doing. It amplifies the work we're doing on the Sustainability Committee. And I hope that you'll come to us with ideas or things that you would like to see happen, and that this can be the beginning of a conversation and an opening for you to come to us and improve our work, deepen our work. And we invite you, we have an open door.
Yes, absolutely. I hope this is just the beginning of seeing more of you and more of your research. We're so happy for all of you. Well, thank you. We again are so grateful and thankful to have this prestigious group of panelists here this evening, and we thank you all for your time and your hard work. For the folks that joined us, please watch out for an email follow-up that will have the recording. We will try to get you a little blurb from each of the panelists about their work, and maybe we can share a photo of some of their research poster. But thank you. Have a wonderful end of your school year. Congratulations again, and enjoy your summer, and have a good night, everyone.
Good
Thank
night.
you. Thank you so much.
Congratulations.
Thank you.
Thank you.
Thank you.
Okay.
Thank you so much for having us.
Yes, our
Bye.
Thank
pleasure.
you.
Take care.